Okay, so here we are for section 8.1. Chapter 8 in general is about right triangles. And section 8.1 deals with the first way we're going to talk about finding missing sides of right triangles, something called the geometric mean. Okay. So we've used angle bisectors, altitudes, medians, all kinds of things. Now we're going to talk about geometric means within triangles as well. So there's still segments within it, but they're going to have this special relationship. So the geometric mean, it's the first thing we have to fill on the sheet here is what is the geometric mean? Well, geometric mean is a part where proportion um, in which the same number, or sorry, when the means of the same, when the means of a proportion, excuse me, are the same number, the number is called the geometric mean of the extremes. So here we go, we have the same numbers here. Okay, these are the means. These are the extremes. They're two different numbers. We call these guys the geometric mean. Extreme and mean, mean and extreme. Now what ends up happening is to solve a proportion, remember we cross multiply. So we're going to multiply a times b, and then we're going to multiply x times x. So what you can see down here is a over x equals x over b, cross multiply, x times x is x squared equals ab. So how do you solve that? Well, you take the square root of both sides. So the quick, easy way to find the geometric mean of something is to multiply the two numbers together and take the square root. So here's the book's example. 9 and 4 are a and b. Their geometric mean is 6 because 9 times 4 is 36. Square root of 36 is 6. Okay. So here's another example. 8 and 10. Okay, so find the geometric mean between 8 and 10. Now, we multiply them together. 8 times 10 is 80. Then we'll take the square root of 80. And this is something new this chapter. They make us go back to some old Algebra 1, simplifying radicals. So really, 1b here that we have to do, I'm going to have you guys, I'm really just walking through it to show you how to do it quickly, but also to go through our old rules of how to simplify radicals. So like before, in a second here, I'm going to click this button and they'll tell me to pause it, and then I'll throw up a question, the question for you, which is 1b, what's the geometric mean of 12 and 15, and then, I'll go through it. Okay, so here we go, geometric mean of 12 and 15. So the formula, again, is really easy. It's just take the two numbers, 15 and 12, and multiply them together, and then simplify the radical. So 15 times 12, 180. Okay, now the unsimplified version is the square root of 180. The easiest way to do this afterwards, unless you're really, really good at having these guys memorized, is realizing that in order for something to have a perfect square root, like 4, which is 2, that's because it's got two 2's, and two 2's are 2 squared. Okay, so we'll talk more about this in class, definitely, but the easiest way to find your geometric mean is actually just to go through, or to simplify a radical, excuse me, because this is the geometric mean, just unsimplified, is to break this down. So like, for instance, 180 is 10 times 18. And then 10 is 2 times 5, 18 is 2 times 9, and 9 is 3 times 3. Now mark out all the non-prime examples, and I'm looking for things that square, which means I'm looking for 2 of some factor. So in this case, I have 2 3's, which means I have 9, because 3 times 3 is 9. Well, the square root of 9 is 3. Okay. Then I also have in this problem 2 2's. Well, 2 times 2 is 4. Okay, so the square root of 4 is 2. So that's a 2 that makes it out. And they cancel off. And then I've got one lonely factor left over in this one, which is a 5. Poor old 5. 5 doesn't make it out. So 5 doesn't have a pair, so he stays inside of the square root. Okay, so in the end, our simplified example is 6 root 5. Now I do want to make sure I'm clear about this. 180 is the geometric mean, but it's not the simplified geometric mean. The simplified geometric mean is 6 root 5. And again, you should have done some of this in Algebra 1. I know you did, if in fact, because it's in Algebra 1. But if you've really, really forgotten and this made no sense to you, come in the morning, or we're going to go over some of it in class. But you'll need to be able to simplify radicals in this chapter. You won't just go, oh, the decimal approximation is this. It'll have to be simplified. Okay, so hopefully that made sense, and hopefully you're ready to move on. So the next part about this is a triangle, okay, and specifically a right triangle. And it's the first theorem in the section, theorem 8.1. And basically what 8.1 says is if you take any right triangle and you draw in an altitude, but the key is you draw it in from the right angle to the hypotenuse. That's the key to this. Okay. What ends up happening is you get three similar triangles. You get the original big right triangle, and then you get the two smaller ones here and here that piece out to those two, and all three of them are similar. Okay. So I'm going to take a minute on the next slide and kind of show you how we know that. So the key to this is the fact that when you've got these triangles, this is how I do it at least, mentally. Okay. Got my original triangle, and it's got its right angle. Make it stand out a little better. And then what happens is it also has two acute angles. That one's in blue, and I'll do this little double one in red. Now here's how I do it. And I've gotten good enough at this over the years I can mentally see it now. But for you guys, especially at first, here's the easiest way to go about this. Don't draw it like the book did it. This tends to confuse people. What you do instead is you draw two triangles just like this one, just smaller. Okay, where you put the right angle then in the same spot, okay, which if I go back to the big drawing is right here. Okay. And then, and this is the key, the big triangle has the single blue and the double red, but this guy right here only has the single blue. So on one of these triangles, just put in the single blue. Okay. The other triangle, the small guy, which will be this one here, doesn't have the single blue. That's in the bigger triangle. It just has the double red. So put the double red in its bottom corner. Okay. And now what happens is these three triangles all match up. So the big one, the single blue is A, the right angle C, the double red is B. Well, for the medium-sized guy, this one here, the right angle is D. Oops, sorry. The right angle is D, so it's a D here. The single blue mark is A, okay, and the leftover point is C. Okay. So that, sorry, I can't quite fit in there, can I? So again, single mark for the medium-sized triangle in blue was A. The right angle actually is D, and again, this is what happened is this triangle got flipped and turned around. That's why it's here. And then the then the C is just the leftover part. For the littler guy, the right angle is again at D. If I draw it in here, I'd draw over that red part. It's right there, but this is D here. B is now the double red mark, so it's B. And then again, what happens is we split up C in this drawing, so here's C over here. And so what ends up happening in the original drawing is this is really also congruent for the single mark. This guy here is congruent for the double mark. So C is double mark on the bigger one. C is smaller single blue mark on the medium-sized one. And now triangle ABC corresponds to ACD and CBD. And here we go. ABC, ACD, ABC, CDB. Now that's important for us because it's going to lead us into our next couple theorems. But the first theorem is this. When you have this triangle, it creates three similar right triangles. Okay. All right, so example 2b then. Okay, example 2b is just, hey, draw the three triangles. So again, here's how I go about doing it. Try to make this as quick as possible. I have the big triangle with the right angle here, and then okay, I just draw two more triangles just like it, just a little smaller. And I put the right angle up in the corner, which here you can see it's right angle here, so both of those guys are going to be T and T for the right angles. Then I put a single mark on one angle, put a double mark on another. Now, this triangle here, STQ, only has the single blue mark. This triangle here, STR, only has the double red mark. Okay. and then I just fill in the letters. Okay. Single blue is with Q. Leftover is S. Double red is with R. Leftover for that guy is also at S. Okay. So now I can say triangle, I don't know, QRS, similar to triangle SRT, similar to triangle QST. There we go. Okay. All right then. Now, again, like I said, there are two theorems left. Okay. And basically how these work is that whenever you have, I'll go back to just the book's drawing here for this. Whenever you have, okay, these three triangles, again, ABC is the big one, ADC is the smaller one, and then CDB is the medium one. What ends up happening is, okay, you get three relationships, and I just want you to copy it out, and I'll show you in the drawing how it works in the theorem. But what happens is, notice here, these guys match, these guys match, these guys, I got to draw over it, they match, A and A. So the next two theorems are actually about geometric means. That's why this section is about geometric means. Okay, so theorem 8.2. Theorem 8.2. So the geometric mean theorem, geometric mean altitude theorem. Whenever we have a right triangle and you draw in the altitude that goes from, again, the right angle to the hypotenuse, what ends up happening is every single time the altitude is the geometric mean, and this is the key part, of the two parts that get formed of the hypotenuse. Okay, it goes back again to these drawings here, but it's really easy just to remember. It's easier just to instead of trying to draw it out, just to remember, okay, if I'm looking at the altitude and I have the two parts, altitude is the geometric mean of the two parts. Okay, so x over h equals h over y, or h is the square root of x times y. The next theorem, so pause it if you need to. Okay, the next theorem again goes back to this geometric mean business, but this one's a little more tricky. Okay, so again, we have the altitude being drawn in, but this time we don't even use the altitude. What we do instead is we use the two parts that get created for the hypotenuse. Okay, so again, x and y, just like we had x and y before. But now what happens is, and this is the tricky part, you have to use this whole hypotenuse for this guy. So what ends up happening is we get two possible geometric means. B is a geometric mean, A is a geometric mean. And B is the geometric mean of the hypotenuse, big hypotenuse, and this little small guy that's next to it. So B is next to the small x, there's its geometric mean. Next is that A, the big leg, or the other leg I should say of the big triangle, is the geometric mean of, again, the big hypotenuse and the little small part next to it. Okay. All right. Okay. So here's what I'm going to do. I'm not going to make you guys answer on the next problems. I'm just going to have you say at the end of each one, did you get that example? I'm going to walk you through it because otherwise it's going to be a 30-minute long video to do all this. So I'm going to go through them a little briskly, but hopefully I can, I'm not going to bother simplifying the radicals either. I'm just going to do it quick just to get through it because otherwise this video is going to take forever to do. But these two theorems here are really the most difficult part in the section. So here we go. First, we're going to solve for x. Okay, now we'll go in order alphabetical. You don't always have to, but in this case I can. So here's the key to this. X is a leg of the big triangle. So x, okay, and this is the part that's tough, x is the geometric mean of the whole hypotenuse, which I don't know technically because it didn't give it to me, but I can add them together. So 8 plus 25 is 33. So x is the geometric mean of the small leg part that touches side x, which is 8, and its hypotenuse of the whole triangle. So x equals square root of 8 times 33, which, to be a little lazy here, 8 times 33 is, pull my calculator, 8 times 33, 264. Okay. And again, I'm not concerned with simplifying that one. So it's equal to the square root of 264. Okay. So again, it goes back to that theorem, that last one there, that the leg of the big triangle is the geometric mean of the hypotenuse and the little segment next to it. Okay. All right, now to solve for y. Y is really in the same situation that x was. Y is a big leg of the triangle. Okay. So if I'm going to solve for a big leg of the triangle, that means I have to use the exact same theorem I did for x. So x was the geometric mean of the whole hypotenuse and little segment next to it. Y will be the geometric mean of the whole hypotenuse and little segment next to it. Okay. So again, I'll get out my calculator. Which is 825. And again, I'm not worried about simplifying that. We'll talk about those in class. Okay, so the square root of 825. Okay, z is the last one. And to me, z is always the easiest. This is the easiest of the three forms to have memorized. We look back at the drawing. We say to ourselves, oh, well, what is z? Oh, z is the altitude inside. Okay. And z then is the geometric mean of the two parts of the hypotenuse of the big triangle. So it's 8 times 25. Okay. Which that's going to be then square root of 200. So again, in class, we will go over how to simplify these radicals, but this video got way longer than I meant for it to, but it's just because there's a lot of material. There are 3 theorems, and there are 3 really important theorems, plus the definition of geometric mean.